Dear colleagues, today we present to your attention an article on the topic of mobile face anti-spoofing through privileged multi-teacher distillation under SWAP constraints. Mobile face anti-spoofing faces significant challenges in distinguishing genuine users from various presentation attacks, including print, replay, and 3D mask attacks. The core issues stems from the mobile device's reliance on RGB-only cameras, which lack on the depth or physiological data needed for robust spoof detection. This forces algorithms to infer liveness from the subtle visual cues that are often ambiguous and easily mimicked by attackers. Here, mobile face anti-spoofing models should balance to be accurate and robust against attack, and the same way optimized for strict mobile SWAP constraints. What are those SWAP constraints? Those are about speed, weight, accuracy, and power consumption, which are critical for successful on-device face anti-spoofing deployment. And here we face the trade-off, which lies in the fact that traditional robust anti-spoofing uses depth sensors or RPPG, which are not feasible for RGB-only mobile deployments, leading to the detection gap. In our work, we introduced the novel Privileged Information Knowledge Distillation framework to enhance mobile face anti-spoofing systems. PIQD uses rich privileged information during training to create a robust yet efficient student model suitable for resource-constrained mobile devices. So the main idea is that we use multi-teacher supervision that employs specialized teachers models leveraging diverse modalities like DAPS or RPPG data. We balance between training versus inference. Powerful teacher models with privileged info train a lightweight student on RGB input. Teachers and privileged info are then discarded for an efficient mobile inference. Advantages of privileged information here enhances teacher accuracy and robustness, enabling the student to learn more subtle liveness cues from RGB input. And we are addressing the trade-off by balancing robustness and mobile efficiency by making the student highly robust during training, yet small and fast for mobile inference. We propose to utilize multimodal supervision to teach the student, which will include two teachers. One of those will be temporal teacher, utilizing RPPG, leveraging physiological cues for robust liveness detection. Second one will be geometric teacher, utilizing 3D structure and recapturing artifacts for enhanced generalization. And the third and deployment-ready model will be RGB-only student, which will be compact and efficient to run on mobile devices at inference. And those teachers transfer complementary supervisory signals into a compact RGB-only student model. And to address the concern that our mobile student model has no access to RPPG and DAPS channels, but utilizes only RGB channel, we are going to use loopy methodology. Learning using privileged information is an approach rooted in Wapnick's statistical learning theory. It allows a teacher model trained with a privileged auxiliary information to impart superior generalization capabilities to student model even when this extra information is unavailable during deployment. Unlike traditional knowledge distillation, Loopy leverages additional input modalities, so-called privileged information, only during training to help define a more robust decision boundary. This results in a more generalized and resilient student model, even without access to this privileged information at inference. And the most specific examples in face anti-spoofing about models which are used not on mobile anti-spoofing systems include DAPS maps, which in our case will be a geometric teacher. That's a teacher model that uses depth maps during training to learn the authentic 3D geometry of live faces which are lacked during 2D attack. This guides the student in discerning 2D artifacts from genuine 3D structures even with only RGB input. And the second example is that physiological signals also known as temporal teacher (RPPG). That's a teacher model accesses that RPPG signals physiological cues from live faces which are absent in the text. This teaches the RGB only student to detect dynamic physiological characteristics for liveness from standard video frames. So here is the proposed training objective. The student model is trained with a multifaceted objective function combining different loss components to leverage privileged information. First one is classification loss. This is the standard binary cross-entropy loss applied to the student model's prediction and the true hard labels. It ensures the student learns to correctly classify samples based on its primary input. Second one is legit distillation loss. This component aligns the student's softened output probabilities with those produced by the teacher's models. It typically includes Kolbe-Leibler divergence to measure the difference, allowing the student to learn nuances of the teacher's decision boundaries. And the third one is feature distillation loss. This one is optional and it encourages the student model to learn similar intermediate feature maps as the teacher model. By matching features, the student can acquire inductive biases and richer semantic information extracted by the teacher. So, our optimization goal is to minimize presentation attack detection error respecting swap constraints, which are speed, weight, accuracy, and power consumption. This represents key performance and resource utilization metrics for deployed models. Speed is actually obvious inference latency. Weight is about model size, which is about parameters and memory consumption. Accuracy relates to primary performance metrics, which are ACR and ER in phase anti-spoofing. And power consumption actually is energy consumption during the inference. So for mobile devices, these constraints are critical. Models must be fast, small, reliable, and energy efficient. This optimization objective finds model parameters theta and temperature tau to minimize error while adhering to the swap constraints. Knowledge distillation terms enable shifting the Pareto frontier, achieving lower error rates without increased runtime costs. This allows for the deployment of highly accurate yet efficient models on the resource-constrained devices. And our evaluation targets include what should be done in the feature empirical work to report on. We should measure accuracy, APCR, BPCR, ACR, which are default phase anti-spoofing metrics to measure accuracy, and those should be measured at specified operating points, including cross data sets and unseen attack splits. We should measure speeds and weight for the resulting student model on device latency and model size of the student. Next, we should measure power on both Android and iOS platforms, and we should measure ablations, which actually the effect of each teacher and different distillation levels. And in the end, we should conduct a Pareto analysis to measure accuracy over latency and accuracy over energy curves. So to conclude, our proposed framework offers a pathway to a more reliable and efficient mobile phase anti-spoofing systems. This research has significant implications for enhanced security and various mobile biometric applications, making advanced features more accessible and less resource intensive. Addressing remaining technical challenges such as diverse attack vectors and real-time performance on heterogeneous hardware is crucial for widespread adoption. And our key takeaways are that we decouple training supervision from test time simplicity. We aim to shift the swap Pareto frontier We reconcile laboratory gains with real world mobile constraints. And our next steps in future research include empirical validation on diverse datasets, SWAP-U extensions for uncertainty modeling, fairness audits across demographics, standardized energy measurements protocols, exploration of multimodal knowledge distillation, and investigation into privacy preserving federated learning. Thank you for your attention.